Well, pre-calculus classes, good morning, good afternoon, or good evening. We'll actually go ahead and finish up section 1.3 here today. And one of the things that we're definitely going to go a lot more in depth with are piecewise functions. I know we introduced those the other day with the evaluating functions. One of the things that we'll certainly look at here today is how to graph those. Probably be a review, at least somewhat, of what you did last year in Algebra 2. So, if we give you a piecewise function here, f of x equals negative x plus 1 when x is greater than or equal to negative 1 and less than 1, f of x equals 2 if x is 1, or f of x equals x squared if x is greater than 1. So we can, again, do a few of these just to kind of review over, okay, how do we evaluate a piecewise function? Well, for f of 0, 0 is greater than negative 1, less than 1, so we'll use that one. So it's, well, I guess here, if you want to really show where everything comes from, negative 1. F of 1, well, we can't use the top one anymore, because x is not equal to 1. It's just less than 1 there. So if x is 1, the function simply equals 2, which we'll talk about how that works. And then if we're looking for f of 2, 2 is greater than 1, 2 squared is 4. So we can actually even use these values as we set up our graph. So I always like, when I'm graphing a piecewise function, to set up a table of values for each part. So for this part, you always have to include the boundary points, and then I also usually like to include a value in the middle. Even though x can't equal 1, we are going to use it on our table. We'll talk about how that works in a moment. Well, when x is negative 1 here, since it is equal, I always like to note I am going to use a closed dot when I graph here, because x is less than 1. I will just have an open dot. So what we can even do is, well, we've already got some of these values, and then when x is negative 1, that's going to be 2. Or actually, for this, when x is 1, I actually have to use the original function. We'll talk about where that comes from here in a moment. So make that correction there. So negative 1, 2 is closed. Now, anything that's in between is always a closed dot. And then at 1, 0, I am going to have an open dot. So basically, we end up with a segment there. Now, for this middle part, this is where we are just going to have one single ordered pair at 1, 2. It is still a function, because if I were to draw my vertical line test, the open dot is not actually included. So I still am only crossing at one point. And then I will go ahead and do one more table for the bottom part. Again, I'm going to start at 1. From there, I can use 2 and 3. Now again, because x cannot equal 1, I am going to start with an open dot. When I plug 1 in there, it's 1. When you plug 2 in, it's 4. When you plug 3 in, it's 9. So when I graph this one, again, I'll have an open dot to start. 2, 4 is there. 3, 9 is there. So basically what we end up with is a section of a parabola. Again, I have a closed dot here, 2 open dots. So again, I still have a function. Now, as far as domain and range, pretty much any time we ask you to graph something from now on, you should always be able to tell us domain and range. So the smallest x value is -1, because it never actually has a gap, just goes to positive infinity. Now, you might even be able to see that just from these. You know, it starts at -1, never has an ending point from there. As far as the range goes, the minimum is 0. There is not a maximum. Now, the only thing you do have to be careful about, the minimum y value of 0 is an open dot. So that is going to be a parenthesis there. So again, you know, you might see some piecewise functions where we ask you to graph as many as 3 separate things. And there is an example of that. Some other things to finish off section 1.3, certainly just kind of interpreting some mathematical verbiage. Write an inequality for each. C is at most 2. So C is less than or equal to 2. M is at least 5. Well, M is greater than or equal to 5. All x's in the interval -2 to 7. Well, that means x has to be less than 7. Greater than or equal to -2. You know, again, going the other direction with it, give a verbal description for the interval below, -2 to 0. You know, here you could say something like x is between -2 and 0. Certainly there are other ways you could describe it. That's one of those, you know, things that would be up to you. As far as an interval including 4 to -infinity, there you could say something like x is at least 4. It's kind of like B up here. M is at least 5. M is greater than or equal to 5. Absolute value, I know I mentioned this the other day. Absolute value represents a magnitude or the distance from 0. So f of x equals the absolute value of x. Because what we're going to do is, certainly I know as you guys have been working into your project even, you know, one of the parent functions you've worked with is absolute value. And we are going to talk a little bit about how you can treat absolute value as a piecewise function as well. So if you have a real number, the absolute value of that number is either a or -a. It's positive a when a is greater than or equal to 0. It's the opposite of a when a is less than 0. Now, one of the things that as you set these up that I always also like to do, and one other thing too, it doesn't really matter which one of these you make the equal to as long as only one of them is. You can't have both equal to, otherwise you don't technically have a function anymore. One of the other things I always like to do is at least talk about, okay, what are the transformations that are involved here? Because that always helps with where this starting amount should be. So for this one, well, if it's -3, it does shift right 3. So your vertex will be at 3, 0. So what that means is we will have 2 parts to this piecewise function. One is x minus 3. The other one is -x plus 3. You just take the opposite of the original function. Now, for this one, it will be x minus 3 when x is greater than or equal to 3. That's where your vertex is. That's, you know, the x value of the vertex here was 0. That's why these are 0. It'll be -x plus 3 if x is less than 3. Now, this next one's kind of tricky. One of the things that you do need to be careful about, And if you want, you can even rewrite it. But you have a reflection over the y-axis. We also have left 7. Now, as far as what that does to the vertex, if you remember, we are going to move it left 7 first, then reflect it over the axis. So that's actually going to put your vertex at 7, 0. Now, we will also talk a little bit about how that impacts. So, again, if you want to use it in the rewritten form, negative x plus 7, well, the opposite's going to be x minus 7. Well, because of the reflection, here the negative x went with the original one. Wherever you have the negative x will be the x's less than 7. For the x positive x minus 7, x is greater than or equal to 7. And here's where, again, it's kind of up to you. If you always like to get in the habit of making the top one the equal to, you can do that. Again, one of them has to be equal to, one of them is not. So that's usually one of the trickier issues that comes up. All right, this next one, x minus 4 absolute value plus 2. Well, for it, what we end up with is right 4 and up 2. So our vertex is 4, 2, which we'll talk about where that comes in a moment. So when we set up our piecewise function, the only part you're going to take the opposite of is within the absolute value. So your two functions actually end up being x minus 2 and negative x plus 6. Now, here's where you do have to be a little careful. 3 and 3, 7 and 7 come from these. The 2 and the 6 are different numbers, but as far as, because it's been shifted up, you still use the 4 for both of these. And so that's why you do have to be a little careful when you have something on the outside. So there is that one. Now, for example 6, you also have to be careful here. This one does have another issue show up, in that it does not shift right 6. It actually only shifts right 3 and up 1. You do have a vertical stretch, which isn't going to impact at least the piecewise function. So our vertex is going to be at 3, 1 if you were graphing this, which again, that impacts your restriction. Now, when you set up your piecewise function here, you don't really need to use the factored version. You can just use the 2x minus 6 plus 1. Take the opposite there, negative 2x plus 6 plus 1. And again, 2x minus 5, negative 2x plus 7. It's kind of up to you. If you do not need to actually show this work, and you can just go directly from here to these, by all means, go ahead and do so. Now, as far as your restrictions, for the positive, x has to again be greater than or equal to 3. X has to also be, for this bottom portion, less than 3. So, as far as the work for these, we do actually have a separate worksheet for this. The first part of 1.3 is still within an assignment in Pearson, but that does complete section 1.3.